0.5 for pentane and 0.3 for hexane, going in at 100 pound mole per hour. And then it says that the temperature is 250 degrees Fahrenheit. And it's to recover a liquid product 90%. It's to recover in the liquid product 90% of the hexane. Then it says find pressure required to do this and the product flow rates.
Okay, so what did you say your approach was?
So first I did was calculate the individual flow rates. I assumed the pressure, since we have the table for the 10 atmospheres.
Okay.
And I found the K value for those. From the K, I calculated the proportionality constant. Because I was kind of using the textbook as my guide. And from there, they had this equation that I don't know if it's applicable to the class. I couldn't find it in my notes that we used to calculate the flow rate per component. So I wasn't sure what exactly is the method of approach for this problem.
Okay, so did you use the recovery of hexane to be 90% first?
I use, so basically what I did was say 90% is coming out as liquid, that means 10% will be coming out as vapor.
No, so that's not actually what it means. So recovery is like a material balance equation. So this means that if you do a material balance, L times, we'll call these will be the X's, right? XP, XP, and XH. These are the Y's. YB, YB, YH. So you gotta watch the wording of the question. So it doesn't say that 90% of the H comes out here. It says that the recovery is 90%. Actually, no, that doesn't mean that.
It says to recover in the liquid product 90% of the hexane. So I'm saying of the total hexane that went in.
Yeah, so,
90%.
okay, right. That's a way to look at it. It doesn't mean that XH is 90%.
Yeah.
Okay, so that's good.
So that means 10% of the hexane that goes in will be
Right.
in the vapor.
Yeah, but that does not mean that YH is 0.1.
Yeah.
Okay. So yeah, that's how I would go about it first.
But I mean, I think like they have like the exact same problem in the textbook, and I was just confused at one of the equations that they used. I was fine until
Okay, what's the equation? We'll see if we can get to it.
it says Fi over Vi equals 9 over alpha plus 1.
9 over alpha plus 1?
Yeah. So what they did in the book was they calculated proportionality constant using the K's that they got from assuming a pressure. So they assumed the pressure.
So guess and check.
Yeah.
Yeah, I think that would be, if you don't know the temperature or the pressure, I think you have to do that.
But I don't know, I don't see that equation in our text, in our notes, so I don't know if that's.
That doesn't look familiar to me either, so honestly, I'm not sure where that came about.
But when I solved it with this method, I got the answer that was on the homework.
Oh, so yeah, I'd be fine with that.
I just want to know if it's legal.
I do not know what this equation is. Yeah.
So if we would try to set it up the way that like John's told us to look at it, we're supposed to use like the recovery of hexane to somehow find the recovery of all the other ones. And he says Kj over Ki depends only on T is given. So apparently we know that. So it's like 1 over Ri minus 1 equals Kj over Ki times 1 over Rj minus 1.
Yeah. That's the equation. 1 over Ri minus 1.
1 over Ri.
Yeah.
And minus 1 is outside that.
Okay.
Equals,
And what is Ri?
those are the recovery, like it's a recovery of one of the components.
Okay.
Equals Kj over Ki. And then times in parentheses 1 over Rj minus 1, again outside of the function. So I guess he was saying we should find all of the other like 2 R's from that. sum of those to find B, or use B to find L. As he says in class.
Yeah, doing it this way is confusing. It's hard to think about that way.
How would you do it, PJ?
All right.
How would you do it?
Recovery of hexane is 90%. So that means L times XH over F times ZH is 0.9. Does that equation make sense?
More than anything else so far.
Excellent. We know these two, right? F times ZH is 30. So LXH is 227, right?
27.
Okay, so that solves that, and then because, like Kevon said, that means 10% has to be in the overhead, so that means V times YH is 3. 3 moles per hour. That's good so far? So now I would probably write similar material balances for one of the other components. So let's pick pentane. Right.
One has in the form of the other two.
Yeah, you could write the other one too if you wanted to. That'd be butane then, right?
Yeah. But can't you make VYB equals to VYP or 1 minus?
Yeah, you could do that.
or
I don't know if that.
100 minus.
I don't know if that simplifies things or not.
We're gonna have two variables to solve for either way. Because we don't have a flow rate or a composition.
Right.
Do you have to K's?
Well, we can guess and check the K's. So that might be that might be a good method. So if you just pick P equals to 10 and see what happens. So that's what you do if you don't know the temperature.
The equation that you wrote last Wednesday, I think, where we have P of composition factor flow rate equals P of composition factor flow rate, then you solve for the pressure. Like, that's the equation that they used for the textbook to solve for the pressure. So they assume the P, and then from that P they got.
Oh, they could just adjust it.
And
Oh,
then
that.
they wrote two equations and figured it out. But it was just weird because I couldn't see how it correlated with our notes, and that was the thing that kind of screwed me up.
Okay. So yeah, that'll happen with John's going up here from memory. So, all right. So the equation from last week was Ki of T in P1 times P1 equals Ki of T in P2 times P2, right?
What they did was the sum of the KI's times the flow rate,
Which flow rate?
the liquid flow rate. So it was like Ki Xi times Li, and they add them all up, and it should be equal to 1 times the pressure. Let me show you. So they did it so right here. So that
they probably get to that through some algebra.
It's what
That's a shortcut if you can memorize it.
That's what what they did, they figured out a proportionality constant for, alpha. So, getting the k's, they divided all the k's by the lowest k value. They got an alpha, and then they had the equation that I showed you that I don't know where it came from. They solved the flow rate from that, and then they did it.
I'm so curious, what page of the book you?
Page 74. Example 2 that I wrote.
Yeah, I personally don't like the sums equations. I just like to think of it this way, and then if I have to get some check, I just do that.
So you would put in a P1, or what would you do?
Well, you have the chart at P equals 10 atmospheres, so I would try that first. And then if that didn't work, you could always guess and check.
And what exactly is your check here, sorry? Like, what are you trying to make equal to?
Your constraint is that these have to sum to 1 and those have to sum to 1. So if you say you try P equals 10 and then you get these that sum up to 1.5, that can't be right. So that'll tell you that you have it wrong. So then you need to go and try another one.
But I mean, we only could guess like 1 p because we have one chart, which is the 10.
Right, but then you can go back and you can adjust. You could say, okay, if I pick 9 atmospheres, then you can go back and repick or recalculate all the Ks. You just have to multiply by 10 over 9. Yeah, okay, so at t equals 250, you have AI 10 ATM. Say this is, I don't know,
I have
2, okay. All right, this will be good.
it's 1.87, 0.94, and 0.48.
Okay, so you try these 3 and it gives you answers that don't work out. So you can go back, you already know what it is at 10, so you can go back and multiply 1.87 times 10 over 9. And that gets you something else. And then you do the same thing.
The book tells you how to do it like with just one try, pretty much.
Oh, okay, I see what's going on. Okay, no, I get it. So, say this is at pressure P that you want to know. So you multiply 1.87 times 10 over P
Yeah, they didn't figure out.
times 10 over P. 0.48 times 10 over P.
What did you do with that? But you have to add up
And then-
you have to have a composition to do it that way, because if you just solve it there.
Right, exactly. So, yeah. So K, remember, is y over x. Is that right? Yeah?
Yeah.
Yeah.
So we want sum of the YBs to sum to 1. That's the constraint. You can't have a composition that's more than 100%.
What do you mean the YBs? Don't you mean like the YIs?
YIs.
So those would.
It should.
What's that?
What would we be putting on the end of this 1.87 times 10 over P equals what?
Oh, well, we don't know what P is, but this equals KV,
Okay.
which we also know equals, or YB. YB is then KB XB. YH is KH. Is this getting too crammed? KH XH. This is KP XP.
I wrote down how to I wrote how to solve it with one try pretty much.
Different than this?
Just the way the book does it, and it's like 6 steps every time.
Okay, go ahead.
So this is from the book, I think it's page 106 for me. So first you guess the pressure. Second, you find all. You find all of these guys. They give you, this is for case 1, which is they give you a temperature and they tell you something about one component in the top and at the bottom, which is what they told us here. So then you guess P and then you look at the chart, the KI chart. And then that's how you get these values. And then step 3 is it just takes forever. Does that make sense? So all this stuff is given, so we're looking at component I. So J is this guy because they told us something about this. So then you go here and then you plug in, you solve for VI. So you sum all the VI's and you get V, which is the bottom one or the top one? The top one for you. And then you use, well, my diagram is like this. Feed, vapor, liquid. So 5, you do like